Hello, here's another couple of questions on nuclear physics, particle physics, radioactivity, things like that. Right, we're starting here with a number of particles. What we got? 5 different things we've made up of quarks. Assume that's a C at the end there. Identify the antiproton from the table of particles. Right, they're giving us the proton at the start, so antiproton has to have all of the anti versions of what's in a proton. So that's going to be C because we've got anti-up, 2 anti-ups and an anti-down. State the value of the charge of particle B. Well, we've got a up and an anti-up, so whatever they are, if you've got particle and antiparticle, they're going to end up being 0. It doesn't matter if we can remember about our ups and anti-ups at all. They're opposites of each other, so that's going to cancel out. B. Nuclei of carbon-14 are produced naturally in the upper atmosphere from reactions of slow-moving neutrons with nitrogen nuclei. And there is the reaction. Identify X. Right, so let's think about the numbers. We've got at the top, we've got a 1 and a 14 on the left, so we must have the same on the right. We've got 0 and 7 on the left, so with a 6, we must have a 1 on the right. So that looks like a proton to me. Carbon-14 has a half-life of 5,700 years. Molar mass is that. Total activity of carbon-14 on the Earth is estimated to be that. Right, estimate the total mass. Right, okay, we've got a lot of numbers to work with here. So our activity, so that's the number of decays per second, is the number of nuclei and multiplied by the probability of each one of them decaying each second. We also know that this decay constant here, our lambda, is log 2 divided by the half-life. That's something we've shown quite a few times in previous videos. So that's going to get us n, which is the total number of nuclei. But then off of that n, we need to then say, well, how many moles have we got? So we're going to need to then divide by Avogadro's constant. That gives us the number of moles. And then we need to say, well, how much mass have we got in total? So we'll have to multiply by the molar mass. So our total mass is going to be our total mass is equal to the number of moles multiplied by the molar. That's not the number of moles, that's the number of nuclei, divided by Avogadro's constant, which gives us the number of moles. So that's 6.02 times 10 to the 23, and then multiplied by our molar mass, which is 0.014. And we know that n we can replace with A times the half-life divided by log 2. So we've got 0.014 divided by 6.02 times 10 to the 23. We need to multiply that by A, which were, what's that, 1.1 times 10 to the 19, and divide by log 2, and also multiply by the half-life. And the half-life is going to be a bit of a pain. So the half-life we've got as 5,700 years, so we need to get that into seconds. So that'll be multiplied by 3,600 times 24 times 365 and a quarter. So that's a lot of stuff to type in to the calculator, which I've already set off doing. I'm sort of stalling for time here while I'm typing stuff in, and it's come out at 6.6 times 10 to the 4 kilograms. That is our total mass of carbon-14. Right. So that's B done. C. Energy in the core of a nuclear reactor is produced by induced nuclear fission of uranium-235. Explain what is meant by induced nuclear fission. Right, so it means that, so it's been initiated by the slow-moving neutron, being captured by, I'm going to run out of space, I might just say this, captured by uranium-235 nucleus, which then becomes unstable and splits and divides. So yeah, induced is the fact everything's sitting there relatively happily until this slow moving neutron turns up, and then that's what initiates the fission. Many nuclear reactors use uranium-235 as fuel. Some of these reactors use water as both coolant and moderator. The control rods contain boron-10. Figure 6.2 shows part of the inside of the core of a nuclear reactor. Explain the purpose of using a moderator and control rods. Right, okay, so the moderator is we're trying to slow these neutrons down. So nuclear fission. So fission produces fast neutrons, and we want slow neutrons. Fission produces fast neutrons, moderator slows them down, and then that means they've got more chance of inducing fission in other nuclei. Leads to more chance of fission later on. So yeah, turn what I said into a sentence. So yeah, fission produces fast neutrons, moderators slow down the fast neutrons into slow neutrons, and those slow neutrons have got much more chance of creating another fission event. Whereas control rods, that is controlling the number of neutrons. So the more you push the control rods in, the more neutrons they absorb. So it slows down the number of reactions that we're getting. If you remove the control rods, it will increase the number of reactions because fewer of those neutrons are being absorbed. So that's what's going on with control rods. Control rods are controlling the number of neutrons. So again, turn that into a sentence. So yeah, quite a nice question to get started. All right, next we have the diameter of a nucleus is about 10 to the minus 14 meters. Complete the sentence below. Diameter of a nucleus is how many times smaller than the diameter of an atom? Right, this is something you just need to remember, really. So we're looking at maybe 10 to the 4, 10 to the 5, something like that. So let's go with 10 to the 5. That should be okay. Obviously, it depends on the atom. Very high energy electrons are diffracted by the nucleus when they have a wavelength similar to the nuclear diameter. Estimate the momentum of an electron with a de Broglie wavelength equal to the diameter of the nucleus. Right, again, another thing that I haven't covered in the videos yet, but in case you have, the de Broglie wavelength is the Planck constant divided by the momentum. So, well, they've given us everything here. Well, they've given us the wavelength, so we just need to rearrange that and then work out Planck constant divided by the wavelength, which they've given us as 10 to the minus 14. So that is going to be Planck constant that's the really small one, 6.63 times 10 to the minus 34, and then divide that by 10 to the minus 14. So that's pretty small, 6.6 times 10 to the minus 20, and its momentum, so mass times velocity, kilogram meters per second. Right, so that's good. Suggest why the speed of these electrons cannot be calculated by dividing that answer by the mass. Well, we've got relativistic effects going on here. These are very high energy, so you're going to have relativistic, blimey, relativistic. Well, how many times do I want to try and spell that? I missed out the first T. I think that was what was confusing me. Relativistic effects. So remember, you've got, if things are moving fast enough, then we're getting enough energy from the kinetic energy that's adding more mass to that particular particle, and that's what can go on. So our total mass is our invariant mass plus the relativistic mass, and that's what we're going to get when it says they're very high energy electrons. So yes. B, the table of figure 5.1 shows some isotopes of phosphorus, and where they are unstable, the types of decay. State the difference between each of the isotopes shown in the table. Right, so they're all phosphorus, so they've all got the same number of protons. This is the number of neutrons, which is changing for each one of them. You can see that the proton number's changing, but staying the same, but the nucleon number is just going up. So we're getting more neutrons. Describe the structure of the proton in terms of up and down quarks. Right, so proton is up, up, down. Describe what happens in a beta plus decay using the quark model. Right, so beta plus is something where we're going proton goes to neutron plus positron plus electron neutrino. But we need to show this in the quark model. So we need to show that we've got an up going to a down plus a positron plus an electron neutrino. Describe what happened. Oh, that's what I've just read out. Just done that one. Should be crossing these off. State two quantities conserved in beta decay. Well, everything. I mean, you can name pretty much whatever you want. So let's go with charge and momentum. But you could have lepton number, baryon number, nucleon number. I mean, you know, you just spin. I mean, whatever you want. Everything gets conserved in all this stuff. So that's fine. Examine the table of isotopes. Suggest what determines whether an isotope emits beta plus or beta minus. Right. So we can say if we've got too many neutrons, then we've got beta minus, and if we've got too few neutrons, then we've got beta plus. I don't know where I'll come up with this from. This is a new bit of notation now. I don't think I've ever used that before. So let's go with too many and too few on those. So yeah, you can see what's going on here. We've got too many of them here, so we're getting beta minus. We've got too few of them there, we get beta plus. And as that happens, we're just shifting you know, one way or the other on all of this. Yeah, we've just seen the beta plus here, where the protons are then creating these neutrons from the beta plus. So you won't end up with phosphorus anymore. You know, same in both of these cases, but it's moving to a more stable situation. So it's moving towards stable rather than that particular isotope of phosphorus. Right, I think I'll make this the last one in this block. Explain what is meant by the statement radioactivity is a random process. Well, there's two different ways you can look at the randomness. So that's you can either say it's impossible to predict which nucleus will decay next. So that's if you're looking at the whole sample and saying, okay, well, let's pick. We got all of these nuclei sitting around. Which one's going to decay next? No idea. It's going to happen at random. So that's one way of looking at it, by looking at the whole sample. Or you can look at a particular nucleus and say, well, I don't know when it's going to decay. So you've got a which if you're looking for the whole sample, and a when if you're looking for one particular nucleus. Either one of them we can't answer, both of which they're happening at random, whichever one it is. Uranium-235 was present during the formation of the solar system, including the Earth. The percentage of the original amount remaining is 1.1%. Half-life is 7.1 times 10 to the 8 years. Calculate the age in years of the Earth. Okay, so we've got our decay equation for our radioactivity. So N is N0 e to the minus lambda T. N over n0 they've given us as 1.1%. So 1.1 over 100 is equal to e to the minus lambda t. They've also given us the half-life, and we know that the decay constant is log 2 divided by the half-life. So 711 times 10 to the 8 multiplied by everything we have to do to turn that into seconds, because that's in years. So t is going to be, so we want to do our natural log. I'm going to flip this upside down to get rid of the minus sign on the power. 100 over 1.1 and then divide by the decay constant. So our decay constant, I'll work that out first. Snapping all of this in, so many blinking numbers. I really need to write down seconds in a year somewhere. I have that on a lookup. So 3.09 times 10 to the minus 17. And then when we multiply that, or we take the reciprocal and then multiply it by this log, we are getting 1.46 times 10 to the 17 seconds. So let's put that back into years. So in which case, didn't necessarily need to, maybe I should have just left it in years. I didn't need to change it out into seconds and back again, really, did I? Could have done the whole thing in years and it would have saved me a lot of trouble. Anyway, right, it's nice to think about that now. I mean, this is a correct answer, but I suppose if they've given you stuff in years, you might as well give the answer back in years. So this was all a waste of time typing all the stuff that I put in the first place, because I'm now just going to divide by all of that in order to go back to years again. So 4.6 times 10 to the 9 years. Yeah, okay, I wasted a bit of time there, but yeah, just leave all of that bit off, and then you just go straight to that answer then in years. If you don't put that bit in at the end, you don't have the decay constant in seconds to the minus 1, you have it in years to the minus 1. Right, figure 6.1 shows the variation of binding energy per nucleon against nucleon number A. Estimate the value of the nucleon number with the most stable isotope. So the most stable one is the one that has got the highest binding energy per nucleon. So let's say somewhere around here. So I don't know, let's say 55 as a guess. Use that to explain why nuclei of this particular element cannot produce energy by fusion. So this is by nucleon number. So this has got nucleon number of 100 here. So we are there. So if we're going to be fusing these, that means we're making stuff which is heavier. So fusion would mean that our binding energy per nucleon would have decreased, which means that energy must be added. Yeah, the only way we're getting energy out is if we're moving to higher binding energy per nucleon, which is either splitting and going from right to left, or fusing and going from left to right. But we've got this definite dividing line at the most stable case. The mass of a beryllium nucleus is that. Use the data provided on the second page of the formula booklet to determine the binding energy per nucleon. Oh, right, okay, so I'm going to have to go away and look up the numbers, so give me a second. Right, so I'm back from looking up the numbers. So we need to look at what our mass defect is. So we need to do 4 times the protons and then 4 times the neutrons, because that's what we got, 4 protons and 4 neutrons. So we got 4 times 1.673 times 10 to the minus 7 plus 1.675 times 10 to the minus 27. So that is all of our sort of invariant mass that we've added up, the component parts. Now, if we take off the mass when they're all bound together, which will be a little bit less because they're in that potential energy well. They've got negative potential energy. That's going to be our mass defect. And that is our binding energy. So the binding energy, once we've multiplied it by the c squared. So the binding energy is that mass defect times speed of light squared from our A equals mc squared. So the binding energy is equal to that. That's our mass defect. So we've got a binding energy of 9.18 times 10 to the minus 12 joules. And what is it asking for? Binding energy per nucleon. So we need to divide that by 8. Gives us 1.15 times 10 to the minus 12 joules per nucleon. So yeah, same thing again. We're looking for a mass defect. We're turning that mass defect into an energy by using E equals mc squared. And that is the energy that ends up getting released. So yeah, so that brings the end of another set of 3. These questions are all more or less the same. There's a very limited number of calculations that you can do in this particular section. So it's just getting fluent in that set of calculations.